Alright, so we're going to continue talking about representations. So let's create a way to describe a construction to get lots of representations. But here it's going to require reviewing some material about linear algebra. So we were talking about n by n matrices. But there's also this notion about linear transformations on a vector space. Invertible linear transformations from a vector space to itself. This also forms a group under composition. And so what are the relations between these two things? Well, if you have a vector space, and a linear transformation, if you fix a basis for your vector space, here I'm assuming the vector space is finite dimensional, dimension n specifically, then one of the theorems from linear algebra is that there exists a unique n by n matrix A such that you can compute the L of any vector by just multiplying that vector by A. And so this defines a transformation sending L to A from the general linear group to the n by n matrices. Notice it depends on the choice of basis. And you can go backwards. So this actually is an isomorphism, so we usually we'll choose to identify the two, and the difference between the two is whether or not you've fixed a basis. So this is the group you work in when you don't have a favorite basis. This is the group you work in when you have a favorite basis chosen. And so why do we care about that? Well, because sometimes there are obvious choices of representations here, and sometimes there's obvious choices here. And so sometimes in representation theory proofs, we will work over here instead. So that's one remark. All right. And so then they sometimes refer to this as being a G module. A vector space is a G module if G acts on V and this action is linear. For all G in the group, scalars alpha and beta in the scalar fields, all vectors in the vector space. Why would you care about such a thing? Because that means that you don't just have remember before, if G acted on a set X, this gave rise to a permutation representation. In our case, the fact that it's also linear means that you actually have a homomorphism to the general linear group on that vector space, not just permutations. So sometimes instead of describing matrices explicitly, what you will often see done is a description of the V module structure. And so just like the case of group actions, the point is to every group action, you immediately have a group homomorphism. I say all that just so that I can look at this example. So let G be a finite group. Let H be a subgroup. Then what we're going to do is look at a vector space like of this form. What this means is that the basis of this vector space are cosets, GH. So this might be a new concept for most students, but you can always form a vector space out of any finite set. It just means you're taking linear combinations of the elements of that finite set. So for instance, let me do the simplest example. K is Z mod 2Z. Admittedly, this is kind of cheating because this is also a group, but this is going to have basis. The cosets are 2Z and 1 plus 2Z. So then the elements here are all things of the form alpha 2Z plus beta 1 plus 2Z, where alpha and beta are just scalars in your field. So it's a vector space of dimension 2. And you've just chosen to name your basis vectors as cosets. Now remember, G acts on G mod H. By doing this calculation. Earlier in the semester, we saw how that would give rise to a permutation representation. Well, since you've taken a vector space with this as its basis, you can extend by linearity. Which means that G is going to act on this formal sum in the obvious manner. And that's going to be a group action on this vector space that is linear by construction. In fact, actually, you can do this in general. If G acts on a set X, you can create a vector space with basis X. And then G acts on this new vector space. In fact, this vector space is a G module. The whole point is that instead of getting a representation into a symmetric group, you're now getting a representation into a general linear group. The whole point is that instead of working with permutations, you're now replacing those permutations with their corresponding permutation matrices. And while right now that seems like a dumb idea, you will see when we get later into the theory that that's actually very useful, because it's hard to decompose permutation groups into smaller groups. It turns out you actually have much more power when you have linear algebra. When you have matrices, there's permutations, there's certain things you can do. When you have matrices, there's things called eigenvalues and all sorts of other types of theory that you can apply. So there's more power on this side. And so this construction actually is a good idea. All right, so we have this notion of vector spaces. Suppose you have a linear isomorphism between two vector spaces. And suppose you actually have V and G were both V and W are both G modules. What if it behaves well with respect to this linear isomorphism? Then we would say that V and W are isomorphic as G modules. A simple example that I care about, or we're going to care about here, is this notion of change of basis. From a vector space to itself. This is a very common concept. If you have two bases, E1 through En, and F1 through Fn, then there does in fact exist a unique linear transformation sending the EI's to the FI's. And you can use this to get from one group action to the other, to create a new isomorphic group action. Namely, of course, you would just define things invertibly. The point is you could define L inverse act on G and then compose with L again. This would be a perfectly fine thing to do. And we'll call this G prime. We'll let it be this thing. And you can check that this is also a group action. And gives you another representation. At the level of GLN, what am I talking about? I'm saying that if you have a representation and an invertible matrix, you can always create a new representation by conjugating by that matrix. And as far as representations are concerned, we don't care about this distinction sometimes. We'll eventually see that there are cases where it's worth making the distinction. But we're going to say these are equivalent, and one thing we'll probably want to prove soon is that these two equivalence relations are actually the same. So the representations you get here are going to turn out to be equivalent. So, the problem is, given a group, determine all its representations up to isomorphism, then you're really just determining up to this equivalence relation, up to conjugation by matrices. Alright, well let's start to look at these up to equivalence. Well, of course, it turns out if you just conjugate by a 1-by-1 matrix, that means you're just multiplying by a scalar. And then since multiplication is commutative, you just get Vij back. So, in other words, every single last one of these representations is equivalent to itself. And so we see that there are n distinct representations up to equivalence. V0 to phi n minus 1. So I guess we're going to want to look at the dihedral group next. And so before I was saying the idea where you send r to an exponential and then you send t to either plus or minus 1. But one thing I neglected to point out that we should have in the previous video is we still need to check which options actually give you a group homomorphism, because these are the conditions you need in order to get phi r to the n to be 1 and phi I t squared to be 1. But we know there's still one other relationship for the dihedral group. And we got it's SR S inverse is equal to R inverse. So that means we're going to want phi IS, phi IR, phi IS inverse to be equal to phi IR inverse. Well, that means whatever this thing is going to be either plus or minus 1 times e to the 2 pi I over n times plus or minus 1. Note it's going to be the same sign because negative 1 is its own inverse. It's going to be e to the negative 2 pi I over n. So now we see that one thing we should have checked carefully is that you need e to the 2 pi I n to be equal to its own inverse. Well, there's only two roots of unity that are equal to their own inverse. That means that either they're going plus or minus 1. And notice the minus 1 only happens when n is even. So we actually see when n is odd, the only option is plus 1, which means that there are only two one-dimensional representations. Namely, the one that sends the trivial representation, that sends everything to 1, and the representation that sends r to 1, and s to negative 1. On the other hand, when n is even, we see that there are 3, because there's the 2 we just had, and then there's also the representation that sends both elements, both generators, to negative 1. So that's it for one-dimensional representations. Let's look at two-dimensional representations. We already discussed the representation where you send R to this matrix, cosine of 2 pi over n, down the diagonals, and the sine to the 2 pi over n. One of them has to be negative. Turns out it doesn't completely matter as long as you're consistent. And then S gets sent to this matrix. This was a two-dimensional representation. It's not the only one. as an example of another representation, you could also send r to cosine of 2 pi times I over n for any fixed integer I. And still send S to this matrix. So in other words, you're treating R as if it's rotation by R to the ith power. It'll be interesting to check, and we will in a later lecture, that you do get a bunch of different representations from this approach. But for now, it's worth pointing out conjugating by one of these is definitely not going to get you the same matrix from earlier. So in other words, in this case, let's just pick the negative matrix. You're not going to be able to conjugate. Or maybe you will. Is it possible to conjugate this matrix to end up with one we had before? If you get out your trig identities, you might realize it's possible and use your even and odd conditions. But on the other hand, if I replace negative with, say, cosine of 4 pi over n, for instance, so I'm just making I equal to 2, and I ask the same question. And is there a matrix I can conjugate this by to get another copy of that matrix? And at the same time, still get this matrix to be the same. Then these would be equivalent representations. If not, they're not the same, they're not equivalent representations.